Hello, myself Swaroopa. I will be presenting my project which is monitoring crop health using drone images. The images captured from the drone will help the farmers in monitoring the health of sugarcane plantation. I will use convolutional neural network to develop an image classification model. This model will help detect if any of the sugarcane plant is infected. The image classification model will classify each leaf image into one of the five categories. The categories are healthy leaf, infected by rust disease, infected by red rot disease, infected by leaf scale disease, infested by sugarcane woolly aphid. For this project, we are considering this four most commonly found diseases. First is rust disease. The rust disease can be identified by red spots all over the leaf. Sugarcane woolly aphid. Woolly aphid infection can be noticed by leaves covered with white fly-like pastes. Red rot disease. This is a fungal disease which causes large red lesions, which we can see at the center of the leaf. Leaf scale disease. It is a fungal disease which causes random dark brown patches on the entire leaf. Research question and hypothesis. The null hypothesis for this project is that an image classification model cannot effectively detect sugarcane plant disease based on the image of the plant leaf. The alternate hypothesis proposed is that by using powerful deep learning modeling techniques, we can effectively detect plant disease using images of their leaves. Data collection. In this project, a big challenge was collecting images of leaves. This is because I could find couple of images on the internet easily, but to effectively train and test the model, we needed at least 10,000 to 15,000 images. The targeted number of images were captured performing sugarcane field visits. I was able to create a data set of around 18,000 images. Data preparation. To limit the processing requirements, I had to convert the images to the size of 100 by 100 pixels. Initially, I tried to shrink all the images to 100 by 100 size, but this caused loss of important details. Cropping out 100 by 100 pixel size images out of a large image helped in preserving the details. To reduce overfitting, I have rotated each image to 90, 180 and 270 degree. The screenshot on the right hand shows all the four orientation of a single image in one row. Labeling images using one-hot encoding. To use the images with a convolutional neural network model, I had to label the images using one-hot encoding. In this encoding, number 1 is used to show the classification for a particular image, creating matrix representation for each image. Each image is converted into a matrix representation with numbers ranging from 0 to 255. 0 represents a white pixel and 255 represents the highest shade of the color. In the image on the right hand side, black is the highest shade and the matrix is representing higher number of darker parts of the image. Normalize the image data by dividing with 255. Next step of the data preparation is to divide each numbers of image matrix by 255. This normalizes the matrix to have values in the range of 0 to 1. This is required as the convolutional neural network model uses concept of probability and needs values between 0 and 1. Reducing bias by randomized training data. When the testing data was prepared, images of one category were clustered together. This created a risk of bias in our data model. So I shuffled all the categories of images. Modeling. Keras TensorFlow library is used to implement the convolutional neural network. A deep learning convolutional neural model takes an image input in the form of a two-dimensional array of pixels. Each pixel of the image is treated like a number representing the RGB color combination for that. The CNN model used. The diagram on the top shows a typical convolutional neural network model. We can see that the input image is provided on the left hand side. The CNN model works like a pipeline. The image enters from the left hand side and various operations are performed on the image at each layer. As you can see, the first half of the layers is called feature learning layer. This layer extracts various features of the image by updating their weights, also known as filter in the CNN. The below image shows how weights which are in the form of filters in the CNN model are used. The weight play a role similar to weights used in the linear regression equation. The last set of layers in CNN works on classifying the image into one of the desired categories. Now let's talk about feature learning group of layers. First layer is called convolutional layer. The bottom left of the image shows the convolution operation. A part of image matrix is multiplied with a filter with certain weights. The result of the multiplication is added to get a single number. In this diagram, a filter is mentioned as kernel matrix. This operation is performed multiple times till the entire image is covered. The resulting output matrix is smaller in size and hence this operation is called convolution. Every convolution layer uses different weights in its filter, hence capturing different features of the image. Next is ReLU layer. The ReLU layer follows the convolution layer. This layer removes negative number generated in the output matrix. This is done by simply setting negative numbers to 0. The next layer of feature learning is max pooling. This layer is used to reduce the size of matrix without losing important details. This is done by taking the highest value from a 2 by 2 matrix of the image and forming a new smaller matrix from it. The image in the slide shows how a 4 by 4 matrix was reduced to 2 by 2 matrix. Since we retain the highest number, the important features like edges of an image are retained in the resulting matrix. The three layers convolution, ReLU and max pooling are generally repeated 2 to 3 times. The last set of layer is called classification. The job of these layers is to condense the matrices created in previous layers into one-dimensional array. Each number in the resulting array will represent the classification probability of a particular category. Since we have to classify an image into one of the 5 categories, the output of the classification layer will be a one-dimensional array with 5 elements. Let's discuss each layer of the classification one at a time. First layer is flattening layer. As you can see in the below image, this layer converts the output matrix generated from previous layers into one-dimensional array. Next layer of classification is fully connected layer. This layer uses its own weights and multiplies those weights with the input one-dimensional array. This is a complex operation as each element of the output array is created by adding the product of weights and each of the element in the input array. This way, each element of input array is connected to each element of the output array. Hence, the layer is called fully connected layer or deep layer. An important point to note is that weights used in this layer are different than the weights used in the convolution layer. The weights in the convolution layer were used to capture certain features of the image in form of a matrix, whereas the weights in the fully connected layer are used to generate numbers that represent the probability of the input image belonging to a particular category. The next layer of classification is softmax. In this layer, the output from the fully connected layer is converted into a probability number between 0 to 1, which represents the probability that the sample image belongs to a particular class. This last layer gives us the classification result of the CNN. Training the model. The code in the slide shows how the CNN model was created using Keras library. Let's take a look at the code. Here I have used convolution layer, activation layer and max pooling layer. These layers are again repeated, and then the classification layer, flatten, dense, and activation, which is softmax, is used here. After adding this layer, we have to use model.compile. Note that we are using the standard Adam optimizer. This optimizer continuously changes the weight of convolution layer and fully connected layer to improve the classification accuracy of our CNN model. Training with 3 epochs. To start training a model, we will use model.fit function. The first X parameter is the array of training images. The parameter y is an array that contains the class label of the corresponding image in the array X. For example, if the first image in array X is of red rot disease, then the first label in the array Y says red rot. As explained earlier, the images in array X are represented in the form of matrix and labels in array Y are represented in one hot format. Next parameter is batch size, which tells that how many images will be processed before updating a model. 32 is a standard batch size used. Next parameter is epochs. Each round of training using the training dataset is called epochs. I have used epoch value as 3, so the training of a model will be repeated 3 times using the same training dataset. I have used validation split value as 0.2. This means that the model will use 20% of the training dataset for testing its accuracy periodically. Model.save function is used to save the trained model in my laptop. In the output, we can see that with every epoch, the training loss decreases and the training accuracy increases. Same is represented in the graphs shown below. After 3 epochs, I got the training accuracy as 72%. This is a good number, but I needed to optimize the model to try to increase this accuracy even further. I tried multiple methods like using HSV image format instead of RGB, changing the batch size and validation split, but the most effective method was to increase the epochs to 50. With higher number of training rounds, the training accuracy increased to 97.85%. It took around 5 to 6 hours to finish 50 epochs on my laptop. The graph on the right hand side compares the training accuracy of 3 epochs and 50 epochs. 3 epochs is represented in orange color and 50 epochs is represented in blue color. The y-axis represents the training accuracy with 1 representing 100%. X-axis represents total number of times the model was updated in the process of training. We can see that with every round of training, the training accuracy of a model increased until it reached a saturation point. I concluded that this is the best training accuracy that I can get by increasing the number of epochs. Any further increase in number of epochs will not have any significant impact on the accuracy. Now that I have completed the training of model, it is time to test the model with some new images from my testing dataset. I used model.predict underscore classes method to get classification for each testing image. The testing images are provided in the form of an array x underscore test. The method model.predict classes will return the class prediction for each image in the variable predict underscore classes. In the for loop below, I am printing the predicted classes and testing image. Result of testing of the image classification using 3255 testing images. In this section, I have calculated the prediction accuracy by counting number of correct class predictions and incorrect class predictions. The accuracy of prediction was found to be 89.42%. This is very good accuracy. Recommendations. This project used manually cropped images, but when using a drone on the field, there will be practical challenges of image focusing, lighting, the method used for cropping images, etc. For particular use, it is recommended that a lot of training considering all the possible scenarios should be performed before using this model for commercial purposes. Recently, high performance algorithms have been introduced which use CNN underneath but can perform classification on a live video stream from a camera. A few examples are YOLO, Faster RCNN, Maxed RCNN, etc. I recommend to try these algorithms as the drone is a fast moving machine with a limited flight time. Conclusion. In this project, an image classification model was developed for detecting sugarcane plant disease. By analyzing images of sugarcane leaves, the classification model was optimized by increasing the number of epochs to 50. The training accuracy increased from 72.39% to 97.85%. When testing this model with a set of 3255 images, the classification accuracy of 89.42% was obtained. Based on the results, we can reject the null hypothesis and accept alternate hypothesis that we can use a CNN based image classification model for detecting sugarcane plant disease by analyzing the images of its leaves. Thank you.